Hey guys, we are Team 19. Our topic is about using materialized views to speed up data warehouse. Here are our team members. Our presentation will follow this step. First, we will talk about the selection of views. Then, we'll discuss the using views in queries. Next, we'll talk about the view maintenance and the warehouse maintenance. In the last, we will get the conclusion. In this part, I will talk about the selection of views, how it works, and some ways to speed up selections. The most essential issues in speeding up data warehouse with materialized views is to select which views should be materialized. The base for selection and analysis is always the notion of modeling the data in multi-dimensional ways of the cube. The cube stores not just the fact data, but also different hierarchies. The figure from this article shows an example of a three-dimensional cube which stores sales data and its hierarchy. It seems that the more views we materialize, the more likely it is to find the proper ways for answering the query. However, it also means the more space we need to store these views. So it is a trade-off between time and space requirement. For 3 dimensions, all possible combinations result in 2 to the power of 3 equals 8 different aggregations. The number sounds rather small, but does not take hierarchies into account. Even for a small number of features per dimension, let's say 7, pre-aggregating all features combinations would blow up the cube and result in about 10 to the power of 6 combinations. In fact, the real-world problem may be more complex. We do not have enough space to store all views. We need to select some of the views to speed up our calculation based on our limited space. Here are 2 ways for selecting optimized views: greedy algorithm and the empirical selections. Greedy algorithm is like giving a certain amount of the space S, find the best set of the views. The picture from our lecture shows the pseudocode of the greedy algorithm. From the example of this article, the dataset HARU96, it shows that the performance gains achievable with this greedy algorithm is at least 67% of the optimal solutions. An empirical way to select the views to pre-aggregate is monitoring the queries submitted by the users. Based on factors like query frequency and the data value, a number of views can be calculated and materialized, which supports the top number of the query. What needs to be emphasized is that the views which we select can support a bunch of queries, not just one, when the classification hierarchies of the qualifying data is taken into account.
After materializing and selecting views, we need to consider how to transform queries to access these views. This process can achieve better query performance for speeding up data warehouse. Generally, direct match and partly match are 2 methods of using these views in queries. For direct match, a query can be completely answered by one materialized view. Besides, only for standard queries, this technique can be used since it's not possible to materialize a view for every query. For partly match, other relations or views are needed. This method is available in more cases because only parts of queries are calculated with MVs, and the non-matching parts of the queries can or must access raw data. To reduce the number of views should be divided as universal as possible to fulfill the demand of several queries. Projection and selection are not required unless some data are never used because they don't decrease the cost of querying. Then we need to consider replacing relations in a original query by materialized views. For explicit use, the users have to know everything about views and be responsible for data consistency. Thus, this method is not very user-friendly. To avoid these drawbacks in transparent use, query optimizers are extended for detection and usage of the materialized views with which the query performance is best. Besides, a lot of information has to be stored, as metadata to increase transparency. After that, administration capabilities for the materialized views can be enhanced, and it will be possible to analyze the queries and to detect whether a new materialized views will increase query performance.
Section 3 discusses view maintenance. View maintenance is the process of updating MVs in response to changes to the underlying base relations. In the maintenance process, the technique of computing increment V depends on several factors, including type of modification, query language expressions, information available for maintenance, system environments, and moments of update. Detection of changes in the base relations is the prerequisite for maintenance. Different techniques to detect modifications could be applied in different situations. First, if the database system supports triggers, the approach of Sari and Vidum can be used to detect modifications with production rules. With this method, immediate maintenance is possible. The second is log tables. Only deferred maintenance is possible with this method. Third, in cases where source databases are heterogeneous, autonomous, and latency, the modifications have to be extracted by comparing a current source snapshot with an earlier one by monitor programs. Immediate maintenance is not possible with this method. A MV that can be maintained without access to the base relations is called self-maintainable. This property is important for maintenance performance because it does not need to scan huge base tables. An aggregate function is self-maintainable if the new value of the function can be computed solely from the old values of the aggregation and from the changes to the base relations. These functions are called additive. There are techniques to make views self-maintainable. The first is the counting algorithm. Querying the base relation to get the number of derivations can be avoided by changing the definition of the MV. Using the counting algorithm, the numbers of derivations for a tuple in the materialization is added as an extra attribute to the view definition. The second is auxiliary materialized views. Instead of using full outer joins, we can also use some other MVs to make the site of these views self-maintainable. These views are called auxiliary materialized views. Querying these views instead of the base relations increases the maintenance performance for local as well as for derived view maintenance. Distributed incremental view maintenance anomalies happens when one base relation is queried to maintain the view while another one is modified again. These anomalies can be avoided either by compensating the new modifications or by using only self-maintainable MVs. Consistency problems could occur in a system that allows multiple maintenance policies. In order to provide consistent views in this situation, we could develop a model based on the notion of view groups. A view group is a collection of views that are required to be mutually consistent. That is, every MV in a view group relates to the same state of the underlying base relations.
After talking about the view maintenance, we can talk about warehouse maintenance. As you can see, there are two kinds of maintenance, external maintenance and internal maintenance. Because in most cases, changes to source data are transmitted periodically to the warehouse, external maintenance can only be done periodically. After the transmission, the modifications are stored in update table to separate the moments of the transmission from the moments of maintenance. There is one update table for each source relation with an extra attribute to indicate the modification type. Beside the update table, data tables are used for deferred and snapshot views. This table includes the modifications to be applied to the respective views. Most important for speeding up warehouse maintenance is to use only self-maintainable MVs because they avoid incurring the base relation for maintenance and the distributed incremental view maintenance anomalies. Another approach to increase maintenance performance is to use MVs as basis for MMV. So, the generation component has to extract the base maintenance pace in the dependency graph. Due to varying requirements, the state of MVs is often changing. For internal maintenance immediates, deferred or snapshot refresh can be used. To avoid consistency problems, querying the mirror-based relation is not allowed during zero refresh. For the same reason, access to the immediates MVs based on this relation is also forbidden during maintenance. To shorten refresh time, deferred and snapshot views can be used. Snapshot maintenance also fast querying and updates, but queries can read data that is not updated. Unfortunately, in most papers, snapshots are updated only in a time-based manner periodically. In our option, value-based maintenance is even more interesting, especially for aggregations. If the difference between the old value and the new value is insignificant, the insignificant threshold must be defined by the user and stored as part of the metadata. Only if a given threshold is reached, the view has to be maintained. For the reason that mostly heterogeneous and autonomous sources are used in data warehouse, the modification of source data are transmitted periodically in a batch manner to relieve the network. The number of updates sent to the warehouse can be reduced by modification compression, that is, to reduce all modifications for the same tuple to 1. Pre-maintenance technique is to describe to increase maintenance performance by dividing the update process into separate functions, propagate and refresh. The propagate function can be processing without logging the MVs, so querying will not be disturbed. The MVs are not logged until the processing of the refresh function, which applies the modification in the data table to the corresponding view. Therefore, the goal of the propagate function is to do as much work as possible to minimize the time required by the refresh function. With the data table and the parallel processing, every self-maintenance view can be refreshed at the same time.
In this paper, we mainly discuss 3 steps: view selection, view usage, and view maintenance for speeding up data warehousing. Firstly, we consider selecting the right pre-aggregation and then focus on the maintenance of pre-aggregation based on several influence factors, such as type of modification, query language expression, and information for maintenance. Moreover, self-maintainability is important because huge base relations don't have to be accessed. Aggregate functions such as addictive functions, addictive computable functions, partly addictive functions are used to compute it from all values and from the changes to the base relations. Since only a small subset of view definitions is self-maintainable without transformation, the counting algorithm and auxiliary materialized views are 2 approaches that are developed to make views self-maintainable. It's preferable using only self-maintainable deferred and snapshot views to avoid distributed incremental view maintenance anomalies. Lastly, an approach of data warehousing is proposed. These warehouse models can be used to answer any query and avoid accessing the source for view maintenance. Modifications are stored in update tables to separate the moments of transmission from the moment of maintenance, and delta tables are used for deferred and snapshot views. Fully self-maintainable aggregations, the counting algorithm, and partly self-maintenance aggregation are considered for maintenance due to refresh updates. Thanks for listening.